Welcome to the Deep Dive. Today we're plunging into something really critical in software development, portability. Especially, when you want your code to work smoothly across different kinds of computers.
Exactly. It's all about how easily software moves between systems or even different development setups.
Yeah, and people often think just about hardware like processors, but it's also about the tools and the runtime, isn't it?
It absolutely is. And for Ada developers, a fantastic guide is the Ada Quality and Style Guide. We're going to focus today on the portability chapter.
Specifically, the first three big topics.
That's right. Fundamentals, numeric types and expressions, and tasking. Getting these right really helps build Ada code that's, well, adaptable, ready for different platforms, different compilers.
So our goal for you, the learner, isn't just listing rules. We want to dig into the why these guidelines exist. Understanding that helps you avoid the common traps, right?
Precisely. Knowing the why empowers you to write code that's robust, adaptable, future-proof.
Okay, let's get started with the first section. Fundamentals. What's the first big point there?
It kicks off with obsolescent features.
Yeah.
The advice is pretty clear. If your program needs to last a long time, steer clear of things marked obsolescent, back in Annex J of the Ada 95 standard.
Unless you absolutely need them for, old Ada 83 compatibility.
Exactly. And even then, the guide says you must document why you're using them, make it obvious.
Right. Because these are bits of the language that, after about 10 years of using Ada 83, people realized weren't the best approach. And Ada 95 offered better ways.
Spot on. They were identified as less useful, maybe problematic, and superseded. Relying on them now, well, it's building on shaky ground for the future.
So what kind of features are we talking about? Any specific examples we should watch out for?
Oh, definitely. There's a list. Things like using the short names for predefined packages, like just text IO instead of Ada text IO.
Oh, what else?
Also, those character replacements using for the vertical bar, for hash, percent, for quotes. Reduced accuracy floating point subtypes are another one. And the constrained attribute on private types, the whole ASCII package, the numeric exception.
Wow, quite a few.
Yeah, and also several representation specs like @ clauses for specific addresses, mod clauses, interrupt entries, even the storage size attribute.
It sounds like a general cleanup, really. The designers finding better, more robust ways to do things in Ada 95.
That's the core idea. These are flagged as potential candidates for removal in future Ada versions. Avoiding them helps ensure your code lives longer without major rewrites.
Future-proofing, essentially.
Exactly. They kept them in Ada 95 mainly for backward compatibility, but that obsolescent tag is a big warning sign. There is a small note about Ada text IO float EO and reduced accuracy types, where the output format is tied to that lower precision, but generally avoid them for new, long-lived code.
Makes sense. So staying with these fundamentals, what comes after obsolescent features?
Next up is global assumptions. This is about being smart about what you assume your target platforms will support.
Okay, so setting some kind of baseline expectation, like what's the minimum I can reasonably count on?
That's it, exactly. The guideline is to make informed assumptions. The guide even gives a list of minimum values you might assume for certain language aspects. This helps ensure your code works on a wider range of targets.
Interesting. What's on that list? What kind of minimums are we talking about?
Things like the minimum bits for a standard integer, they suggest assuming at least 16. Minimum decimal digits for a floating point, say 6. Minimum bits for fixed point, maybe 24. Also, things like maximum characters per source line, they suggest 200. Minimum bits for root integer, again, 16. The range for duration, minus 86,400 to plus 86,400 seconds.
That's a day, right?
Exactly. And the granularity of duration small, maybe assume no better than 20 milliseconds. And minimum maximum scale for decimal types. But interestingly, it specifically says don't make assumptions about the character type.
Why these specific minimums? Is it about finding the lowest common denominator?
Pretty much. These values represent what you can likely expect from the vast majority of systems. If you design your code to work within these limits, it's much more likely to port easily.
So even if my system gives me a 64-bit integer, I shouldn't write code that needs it everywhere if I want portability.
Precisely. Stick to the assumed minimums as your requirement. Think of them as practical maximum dependencies. And the warning about character. That's because character sets can vary wildly between locales and systems.
Got it. Aim wide for compatibility. The guide mentions things like 16 and 32-bit embedded processors being common, which explains some numbers, and that duration range is actually from the standard itself.
Right. And it also notes that while Latin 1 is often a reasonable assumption for character, what a specific device can actually display is another story entirely.
Very practical. Okay, next up, comments. We know comments are good, but what's the portability angle?
For portability, the key is using specific highlighting comments for any non-portable features you use, in packages, subprograms, tasks, wherever they are.
Just flagging them isn't enough, though.
No, you also need to describe what you expect that non-portable feature to do. What behavior are you relying on? This is crucial for anyone porting the code later.
Like the example they give a memory map PDO package with big warnings saying, hey, these addresses are implementation specific, and we assume the printer line is 80 chars max.
Exactly that. Those comments are like bright red flags. They tell maintainers, danger zone here, needs attention during porting. And explaining the assumption helps them find an equivalent or understand the limitation on the new platform, especially if the original vendor docs are long gone.
Transforms porting from guesswork to something more structured.
Good tip. Okay, what about the main sub-program, the entry point of our program?
The most portable approach, consider using just a parameterless procedure as your main program.
No command line arguments.
Well, the guide mentions ada.command line, which is the standard way to get arguments. But it warns that its exact behavior, even its specification, isn't perfectly portable across all systems and operating systems.
So if you do use it...
Then the advice is, encapsulate it.
Oh.
Hide all uses of ada.command line inside a specific package, and document exactly how you're using it and what you're assuming about the arguments. Like their environment package example, which wraps up getting an execution mode maybe with a default value.
Right, that isolates the dependency. The thing is, OCs handle command lines differently, number of args, format, whether they exist at all. So for maximum portability, your program should ideally work even with no arguments.
Especially for embedded systems, right? There might not be an operator typing things in.
Exactly. Compile time constants or reading config from a file might be more portable in those cases. The guide even suggests POSIX might sometimes be a more portable alternative than ada.command line, depending on the ada implementation family.
Okay, minimize reliance on the execution environment. That leads nicely to encapsulating implementation dependencies. Sounds fundamental.
It really is. The core idea, to create specific packages just to isolate hardware or implementation-specific code. The key is that the specification of these packages, their public face, must stay the same across different platforms.
Yeah, the interface is stable, but the guts change depending on the target.
Precisely. And if you're doing this for, say, efficiency, you need to clearly state that objective in the comments. Why does this dependency exist?
And you'd have different package bodies for different targets, like Linux versus Windows or different hardware. And they mention isolating interrupt handling tasks, too.
Yes. Definitely isolate interrupt handlers. They are inherently tied to hardware. This encapsulation means most of your code stays clean and portable. Only the code inside these special packages needs changing when you port. And documenting the why helps future developers find alternatives or understand if the goal, like specific performance, is even achievable on the new target.
Makes perfect sense. Isolate the tricky bits. What about features added by the compiler vendor? Implementation added features.
The guideline here is pretty strict. Avoid vendor-specific packages or features they've added to standard packages unless they're part of the official ADA standard or the specialized needs annexes.
Why the caution?
Simple reason. Vendor A's special feature probably won't exist in Vendor B's compiler. And even if Vendor B has something called the same thing, it might work differently in subtle ways. That's a recipe for porting nightmares.
Plus, vendor extensions might clash with new standard features added later.
That's another risk, yeah. Things added after ADA 83 could conflict with standard pragmas or attributes introduced in later versions.
But are there exceptions? When might you need a vendor feature?
The guide acknowledges some cases, maybe integrating with other vendor products, multilingual systems needing specific libraries, or squeezing out critical performance in embedded systems. But even then,
Isolate it.
Isolate it. Put it in a dedicated package, clearly mark it. And there's a nuance. If a vendor gives you a package as source code, and that source code itself is portable ADA, using it might be okay. The danger is relying on compiled, non-standard features built into their specific toolchain.
Okay, so the risk is dependence on the implementation, not necessarily just the vendor. What about the specialized needs annexes?
Yes, systems programming, real-time, distributed, numerics, etc. The guideline is prefer features from these annexes over vendor-specific stuff. but still document their use clearly.
Why prefer them? Standardization.
Exactly. If multiple vendors support, say, the real-time MX, your code using its features will be more portable between those vendors. It provides standard solutions for specific problems.
But there's a catch, isn't there? Compiler support for annexes isn't mandatory.
That's the key caveat. Just because it's in an annex doesn't mean every Ada compiler supports it. So relying on an annex still introduces a potential portability dependency. That's why you should localize its use and document which annexes you need.
Right, so even standard optional features create boundaries. Okay, next. Dependence on parameter passing mechanism. Sounds a bit technical.
It is the core advice. Don't write code that breaks if parameters are passed differently. Ada allows implementations to pass things like records or arrays, either by copying the whole value or just passing a reference, like a pointer.
Pass by copy versus pass by reference.
Right. And your code shouldn't care which one the compiler chooses. Also, if a subprogram has multiple parameters of the same type, especially in out ones,
The ones that can be read from and written to.
yes, you need to make sure your code works even if two seemingly different parameters actually point to the same variable in the calling code. Aliasing.
The examples they give show how output can change based on copy versus reference, and how alias and out parameters can cause trouble.
Exactly. The flexibility given to the compiler means you can get different behavior or even program error if your code implicitly relies on one mechanism, especially with composite types or when inner procedures access variables from outer scopes alongside parameters. Don't assume how it works under the hood.
Are there times you have to depend on it, like interfacing with C or other languages?
That's the main exception. Foreign code often has rigid rules about parameter passing. If you need to interface with it, you might have to rely on a specific mechanism.
So what's the portable way to handle that?
Again, encapsulation. Create an Ada interface package that handles the calls to the foreign code. Export Ada-friendly operations from this package that hide the underlying parameter passing dependency. Keep the non-portable interface details contained.
Create a clean boundary. Makes sense. Last one in fundamentals. Arbitrary order dependencies.
This is about not relying on the evaluation order for certain things in Ada where the standard says the order is arbitrary. A common one is the order parameters are evaluated in a subprogram call.
Like their utilities.unique example. Calling it twice in one expression gives different results depending on which call happens first.
Precisely. Your compiler might happen to evaluate things left to right, and your code works. But another compiler, or even the same compiler with different optimization settings, might evaluate right to left, and suddenly your code breaks.
Even if you didn't intentionally rely on the order.
Right. Unintentional dependencies are still dependencies. So the safe bet is just don't write code whose correctness hinges on an evaluation order the language doesn't guarantee.
Okay, that wraps up fundamentals. A lot of good points there about avoiding obsolescence, managing assumptions, commenting encapsulation. Let's move to numeric types and expressions. Ada is known for being good with numbers, especially for embedded stuff, right?
It definitely is. Strong typing, features for controlling precision, but there's always that inherent tension, that trade-off between using every last bit of machine precision versus writing code that behaves consistently everywhere.
Portability versus specific optimization. What's the first guideline here? Predefined numeric types.
Yeah, the advice is generally avoid using types like integer or float directly from the standard package. Instead, define your own types using range for integers or digits for floating point. Let the compiler pick the best fit based on your requirements, not based on whatever its predefined integer happens to be.
Why is that more portable?
Because implementations have flexibility in defining those predefined types. If your code assumes integer is 32-bit because it is on your machine, it might fail with overflow errors when ported to a system where integer is only 16-bit.
Like the second off day example. Type second off day is range 0.86400 is much clearer and safer than assuming integer is big enough.
Exactly. It states the need directly. And this applies to array bounds, loop ranges too. If you don't specify a type, it often defaults to a predefined integer, which might vary.
But are there any cases where using predefined types is okay?
Yes, the guide mentions a few, like array indices where the type isn't semantically critical, string indexing is a common one, or for pure numbers without units like exponents, simple loop counters maybe.
But not just to avoid declaring types.
Definitely not. You lose the benefits of strong typing then. Oh, and the right side of the operator must be an integer type. Using natural or positive might be okay for things like string indices where those ranges make sense. It's about distinguishing between simple indexing and indices with deeper meaning, like a hash table index where the range might matter more.
And they mentioned maybe defining your own myInteger32 package if you really need a specific size as a base. Okay, what about the accuracy model?
This guideline points towards the Numeric's Annex G. If performance and numerical accuracy are really critical, you should try to use an implementation that supports Annex G.
What does Annex G give you?
It defines accuracy and performance requirements more strictly for floating point and fixed point math. It includes a strict mode for portable numerical results. If your program relies on strict mode properties, it's portable to other strict mode environments. It also gives you attributes to query the underlying model anticipates, exponent range, things like that.
Sounds useful for demanding calculations. What about accuracy analysis?
This emphasizes doing your homework. Really analyze the accuracy and precision your application needs.
Why is that critical for portability?
Because a processor might use extra internal guard digits during calculations, but you can't rely on those guard digits being there on every platform.
So define your types based on the analyzed need, not based on results that might be artificially accurate on one machine.
Exactly. Choose the lowest precision that demonstrably meets the requirements based on analysis. That way, it should work even on less precise hardware.
And that connects to the next guideline. Accuracy constraints don't push the limits of the machine.
Right. Even if two machines have the same number of mantissa bits, their arithmetic units might have subtle differences. Some Ada implementations might give slightly better accuracy than required by the standard. Don't write code that depends on that bonus accuracy.
Designed for the guaranteed baseline, not the accidental extras.
Okay.
And like before, comments are important for numerics too.
Vitally important. Comment the analysis, the reasoning behind precision choices, the mathematical basis. This helps anyone maintaining or reporting the code understand the numerical decisions.
Makes sense. What about sub-expression evaluation pitfalls?
This is about intermediate results and calculations. Ada doesn't require range checks on every tiny step within an expression, but it does check for overflow on the result of each operation.
So an intermediate step could overflow even if the final answer is okay.
Yes, and whether it overflows can depend on the order the compiler chooses to do the calculations or the size of intermediate registers. The DEMU overflow example shows exactly this. 3x. 4 might overflow calculating 3x on one machine, but not another, depending on register size.
Ouch. So you need to anticipate the range of intermediate values and maybe use subtypes, derived types, or factoring to keep them in check.
That's the recommendation. Be proactive about managing those intermediate ranges.
Okay, now relational tests on real numbers.
Yeah.
Comparing floats for equality is famously tricky.
It really is. The guidelines suggest preferring a talk for comparisons and being very wary of talk, and especially.
And use type attributes for comparisons.
Yes, particularly for checking if something is close enough to another value or close to zero. Use attributes like model small or model epsilon to define a tolerance.
Why avoid strict equality? Because of representation errors.
Exactly. Floating point numbers often aren't exact. Tiny errors accumulate. Strict equality will often fail unexpectedly. Comparing if the absolute difference is within a small portable tolerance defined using those attributes is much more robust.
Even for comparing against zero.
Even then, a calculated value might be incredibly tiny, but not exactly zero. Testing against models small or similar is safer. The guide notes this is a common issue in many languages, and Ada gives you tools to handle it portably.
Good to know. What about decimal types? These are more for financial or information systems, right?
Correct. Where exact decimal representation is key. The advice here is multifaceted. First, declare different decimal types for different scales, decimal places, and different units, dollars, euros, etc.
Why different types for units?
And for strong typing. The compiler can then catch you accidentally adding dollars to yen without an explicit conversion. Use subtypes for range constraints, like salary limits. Encapsulate different measures and packages.
Okay. Minimize decimal types for unitless data.
Yes, to avoid unnecessary conversions. And decide, do you want truncation, Ada's default towards 0, or rounding? Use round if you need rounding.
And the big portability point.
Don't use decimal types at all if your compiler doesn't fully support the Information Systems Annex F. The core language support is limited. Annex F provides essential features like guaranteed 18 digits and formatted I/O, text I/O, .editing.
Like the currency example package shows, with different types and conversions.
Got it. Now, quickly on storage control. Memory management varies.
A lot. Especially in embedded systems, you might not even have deallocation. So mechanisms related to storage are often implementation dependent.
And the specific guideline on representation clause for storage.
Don't use storage size in a rep clause to specify memory size for a type. Its meaning is ambiguous across implementations. What exactly it includes isn't fixed. Using it ties you tightly to one vendor and makes porting harder. Treat it as a red flag during porting.
Okay, what about access to subprogram values? Pointers to procedures or functions?
The guideline is simple. Don't compare them for equality. Why not?
Because the standard doesn't guarantee that two access values pointing to the same subprogram will compare as equal. Internal representations, elaboration checks, things can differ. Even getting the access value twice using access might yield values that don't compare equal. It's unreliable.
So avoid equality checks. Any exceptions?
A very narrow one. Maybe define a constant with the access value and compare against that constant. But even that isn't foolproof due to potential implementation differences. Best to just avoid relying on it.
All right, and finally under storage pool mechanisms.
The suggestion is to consider using explicit storage pools if you need fine control over memory. Things like implementing your own free lists instead of using unchecked deallocation, or using Ada's storage pool aspect with allocators for mark release schemes, or even bypassing allocators with unchecked conversion, though you lose initialization.
So taking control can sometimes be more predictable, maybe more portable, than relying on the default implementation strategy.
Potentially, yes. It makes the memory management strategy explicit rather than implicit and possibly variable.
Okay, that covers fundamentals and numerics. Now for the third big topic today, tasking. Concurrency in Ada. How does this impact portability?
Tasking is an area where Ada deliberately gives implementers a lot of freedom. This allows optimization for specific domains, like real-time, but it inherently reduces portability compared to core language features. Behavior can vary quite a bit.
Unless you're using the real-time systems annex, which adds more definition.
Exactly. That annex helps standardize things for real-time work. But these general guidelines assume you might not have full annex support.
So first tasking guideline, task activation order.
Don't depend on it. If you declare several tasks together, the order they start running is undefined by the standard. Don't write code that assumes task A starts before task B.
Makes sense. What about delay statements?
Don't rely on achieving a specific, precise delay duration with a delay statement, and never rely on assumptions about how fast tasks execute or when they get preempted to meet timing requirements.
Why is delay tricky?
Implementation differences. The scheduling algorithm isn't fixed. The underlying clock tick precision varies, so delay 0.1 might result in slightly different actual delays on different systems. Relying on execution patterns is even more fragile.
Okay, and related to time, package calendar, type duration, and system tick.
The guideline: don't assume a correlation between system tick, often a hardware clock counter, and duration from Ada calendar. The standard doesn't require one, even if some implementations happen to link them.
Got it. No assumed link. What about the select statement? Select statement evaluation order.
Don't depend on the order guards, the when conditions are evaluated, and don't assume anything about how the system chooses which open alternative to execute if multiple guards are true.
It's arbitrary.
Assume it's arbitrary. The standard doesn't define the order or the selection algorithm. Your code must work regardless of which guard is checked first or which open path is taken.
Okay. What about the overall task scheduling algorithm?
Don't assume tasks run uninterrupted until they hit a synchronization point, like a rendezvous or protected object call, and use pragma priority only as a general hint of importance, not for hard real-time guarantees.
Because the actual scheduling, time slicing, preemption priorities is implementation defined.
Exactly. It can vary wildly. Synchronization should only rely on explicit Ada mechanisms, rendezvous, protected objects, task dependence, maybe pragma atomic, not on timing assumptions.
And the number of priority levels and how equal priorities are handled also varies.
Yes. The guide notes exceptions for some real-time systems needing tight control, where things like cyclic executives might be programmed, often needing an external clock.
What about the abort statement?
The advice is blunt. Avoid using abort.
Why? Too unpredictable.
Its handling varies significantly across implementations. It's a major portability killer and can lead to messy state issues. Just best avoid it if possible.
Okay. Last one for tasking. Unprotected shared variables in the pragmas atomic and volatile.
Guideline: don't use unprotected shared variables for task communication or synchronization, period.
Use protected types or rendezvous instead.
Absolutely. Use protected types for shared data synchronization, rendezvous for communication. Unprotected shared variables are extremely dangerous in concurrent code prone to race conditions. Behavior depends heavily on compiler optimizations and underlying memory models.
And atomic or volatile?
Use them only as a last resort if you absolutely must interact with hardware or bypass runtime limitations and you fully understand the implications. Protected objects are the standard, safe, portable way.
Okay, wow. That covers our first three major areas from the portability chapter: fundamentals, numerics, and tasking. Lots to think about there.
Definitely. It really highlights how writing portable Ada isn't automatic. It requires conscious effort in understanding these potential variations.
But by applying these guidelines, understanding the why behind them, you, the learner, can really boost the adaptability and longevity of your Ada code, making it work reliably across different environments.
It's a solid foundation. And remember, this was just the first dive into this chapter.
That's right. This isn't the end of the story on Ada portability. We definitely encourage you to join us for our next deep dive. We'll be tackling the rest of the chapter.
Yeah, things like exceptions, representation clauses in more detail, dealing with other implementation-dependent features, and the nuances of portable input-output. Still plenty of important ground to cover.
So as you work on your Ada code, maybe think about where you might be making assumptions tied to your current setup. How could you apply some of these principles encapsulation, avoiding arbitrary dependencies, careful numeric handling to make your code more resilient?
It's a good exercise. Where are those hidden dependencies lurking?
And maybe a final thought to leave you with. How do you strike that balance? The balance between squeezing out every last drop of performance using platform-specific tricks versus ensuring your code is broadly portable and maintainable for the long haul. How does knowing the standard and where implementations might differ help you make those critical trade-offs?
That's the core challenge, isn't it? Worth pondering.
Indeed. Well, thank you for joining us on this deep dive into Ada portability. We look forward to continuing the journey with you next time.